What does the work kinetic energy theorem have to say about the braking distance of a car? So the way I'm going to analyze this is, let me actually redraw another picture of the car here. And I'm going to say, okay, here's a car, okay, and okay, pretend that that's a halfway decent car, and it's starting with some velocity v, okay, but there's a force, a braking force applied to it. Maybe I'll just put the force in this picture. Usually I do free body diagrams, but I'm going to break the rules here and just put the force in right there to recognize that that's a negative work really done there. And then the car eventually later on, that same wiggly car here, I don't know if I can redraw it exactly the same way, but eventually comes to rest. In other words, there is no velocity here. You could say that the final velocity in that sense is equal to zero. In fact, thinking about this a little bit more, maybe I should have called this v naught for the initial velocity. And let's look at the work kinetic energy theorem. So the work kinetic energy theorem is work is equal to change in kinetic energy, which we've seen it expressed as 1/2 m, I think, v final squared minus 1/2 m v initial squared. But in this case, I'm going to express it as 1/2 m, and since 1/2 m is kind of a common factor there, I'm just going to express that as v squared minus v naught squared, kind of adopting the subscripts that I used to use a little more in kinematics. In this case, though, I think the fact that the final velocity v is equal to 0, since the car is braking, its goal is to come to rest, I'm going to say that's equal to 0, but the work is negative. And maybe in this case I can therefore say the work, I can replace that side with minus F times d. So if d represents the displacement, and then that's going to be equal to minus 1/2 m v naught squared. And of course that means these minus signs can cancel out. So that was a kind of detailed analysis there. But okay, if we assume that the braking force is independent of speed, which it turns out for most braking systems in cars is actually remarkably close to being true. So we're going to assume that force is constant. The mass is constant for the car as well. That hopefully should be somewhat maybe trivially obvious, unless perhaps your name is Einstein, I guess. But for the rest of us, I think it's obvious enough. We can take this complicated formula and restate it and say the displacement is proportional to the initial velocity squared. Okay? That would mean, like, if you doubled the initial velocity, what would happen to the braking distance? It would have to be 4 times as long. So that's kind of the implication there. Let's see how that kind of plays out in a series of slides in the answer here, because it says, okay, a car that is initially moving at 30 miles per hour that hits the brake is described by the FBD shown. And that's in a little bit more detail than I had. I ignored the gravity and the normal force in what I did because they're not the ones I was interested in doing work there and then putting into the work kinetic energy theorem, but that's okay. The braking force causes the car to accelerate in a way that slows it down until it comes to a stop. And in this slide, it's claiming that maybe that would be about 40 feet. And it turns out I calculated that based on some reasonably realistic assumptions. In other words, that's within the realm of believability for a real car that at 30 miles per hour, if it slams on the brakes reasonably hard, it could possibly have a braking distance of 40 feet. But then what happens if it's going at 60 miles per hour? What can we predict based on this formula, right? So we just saw 40 feet. Would it be just double that of 80 feet? Well, this says velocity squared, right? So what implication does that have, right? So we're going to assume, again, the braking force is the same, and that implies the same amount of acceleration throughout the process. It says here, since kinetic energy depends on speed squared, because that's really where that speed squared came from, the total amount of it is not doubled, but is actually quadrupled. So this is kind of taking that conceptual perspective that when I bring the car up to 60 miles per hour, I have quadrupled the amount of energy that it has. And the work that the brakes have to do is to remove that energy, basically convert it into thermal energy, mostly onto the brake pads or the rotors or etc. in the braking system, right? If it has 4 times as much energy to do that, and it does it with the same amount of force, it stands to reason it might have to go 4 times the distance. And since 40 times 4 is 160, it makes sense that it would have to be 160 feet, quadrupling again that distance.